everything like check करो. Question? What is visible? Not this one. वो डुप्लीकेट नहीं है शायद, क्योंकि जस्ट डिस्प्ले जा रहा है, हम वो यूज़ कर रहे हैं ना, अभी वो दिखेगा. ओनली बस जस्ट स्क्रीन शेयर होता है. ठीक है. ठीक है, पुराना वाला ऐसे करते हैं. हाँ हाँ ठीक है. वैसे टीम्स वाला में चलते थे. हाँ, तो फिर से वो वाला मीटिंग मेरे उसमें तुम ज्वाइन करो, मेरे में हो जाओ. हम्म हम्म सर इट्स ओके, विल डू इट. टीम्स तो है यहाँ पे, इंस्टॉल किया है ना. जीमेल पे जाओ मेरा, उसमें लिंक है ना, वो वाला लिंक ज्वाइन करो. हाँ, इसमें बट आई थिंक नहीं, तुम वो वाला आईडी से ज्वाइन करना पड़ेगा. जो टीम्स में ओपन करके वो पुराना वाला आईडी है ना, नहीं तो फिर वो लॉग आउट करेगा, मेरे को ज्वाइन करने नहीं देगा. जो पुराना वाला आईडी है ना, उसमें ज्वाइन करना आप. है टीम्स पर कर. इतना बोलो. start meeting. ये वाला copy meeting link करो. ठीक है. Nothing shakes. एक सेकंड, इस पे जब आ रहा है मेरा तब काट लेना इसमें से. देखो मेरा आ रहा है क्या? ये वाला ओपन करना मेरा आता है. ठीक है, मैं शेयर कर रहा हूँ. बंद करो. आ रहा है ना मेरा? ये वाला दिख रहा है मेरा? नहीं, ये आ रहा है ना? हाँ. That should continue. That should not have. Good. उसके लिए वो जस्ट डिस्प्ले यूज कर रहा हूँ, कोई प्रॉब्लम नहीं. ओके, आई थिंक वो ओके. Okay. So this is. Should we get started? I think it's already late, I guess. Yeah? Yeah? Okay, good. Okay. So since many of you are kind of told me that okay, you wanted to leave early, so what I thought was that okay, so I mean instead of going through many details, right? So I thought like we'll only look at some few important things which are really kind of the students has a confusion with respect to Verilog, and then so maybe we'll focus more on the synthesis part. Okay, but of course I'll just kind of pass on the material, and whenever you get time, so we'll just go through it, and if any questions come back to me. Okay, good. So let's get started. So right. So I mean just kind of a motivation slide. Yeah, so this is always I use, and of course I also use it for my the PhD defense. So it's almost 6 years or 15, right? Almost 10 years old slide. Yeah. So basically here what we are trying to really say that, right, so in the past, right, So we were able to kind of or right, our the seniors or whatever, right. So they were able to really build even computers with this vacuum tubes, and of course, right. So none of us maybe studied these vacuum tubes, right. And then the era of the discrete transistor came. I mean, that's where we have, let's say, these discrete transistors, and we were also kind of able to kind of create the let's say the computers. And then soon after that, what is known as the integrated circuit era started, where not only the transistors but their interconnections were started realizing on single piece of silicon. So now we call it as everything is integrated. And then of course, right, the companies like in the beginning, right, so Apollo, Xerox, and of course, right, we know only Intel, but these are the companies they used to really build the PCs, and of course, right, so Intel gained the momentum and then started building Pentium 1, 2, 3, 4, and of course, right, after that something happened, we went into the multi-core era and all. So here the idea is that the transistor density, right, is kind of doubling almost every 18 months or the 2 years. That means maybe the physicist, chemist, or the lithography people, or maybe the fabrication equipment people, right, everybody is really working towards only single aim. How could we really kind of reduce the size of the transistor so that we can pack more and more, and if you have more transistors, it's more powerful, we can do multiple things. That's the idea. And actually, right, so the Moore, right, it's a not a kind of law or anything, but it's a more of an observation, right. So everybody is really working in a kind of tandem to really increase the count. And now from our perspective, what is important is that, okay, so this electronic design automation tools, right. So right, so here, I mean, since we kind of decrease the transistor sizes, right, definitely the distance between your source and drain will definitely decrease, and again you see, right, the distance is decreased, right, of course, right, the speed is almost constant for the electron, right, and then of course definitely the time will decrease. So ultimately the clock frequency goes up, and that's where it started shooting up the clock frequencies. So maybe go back and check. So what are the frequencies of the Intel Pentium 1, 2, 3, and 4? Okay, good. So here, so electronic design automation really plays a kind of a vital role. Okay, now let's say, I mean in the lab also, right, if there are multiple components, right, at some point of time connecting wires on the breadboard will be really difficult and it will be messy, right. So here the same thing, right. So we are trying to deal with millions and billions of transistors, right. Suppose if I ask you, right, so you wanted to draw a full adder, perfectly fine, it fits in a kind of a piece of paper. But now if you wanted to really draw a kind of the diagram of the complicated processor what we have today on a piece of paper, it would be really tough, right. So basically, right, so these electronic design automation tools will really help us to really kind of design block by block, and maybe they help us really kind of comprehend the designs, right. So that's where this era of VHDL, Verilog, and of course, right, the front end tools, back end tools really started emerging. And now if you see, right, without those tools, I mean you see, right, we won't be able to kind of do much today, right. So that is really the importance of the kind of electronic design automation industry. And again, of course, right, I will say that synthesis tools are really the kind of at the forefront, right. So maybe you write your Verilog or VHDL design, but of course, right, we need someone or some tool to really translate that Verilog design into some kind of a gate level netlist, right. So the synthesis tool is the first tool we will try to use. Okay, good. I just wanted to really motivate that. Okay, so this electronic design automation tools or this industry is also kind of one important industry, those who are looking for the career in VLSI. Okay. So as I said, so I will not go into the kind of each and every details of the language aspects, and I'll just kind of pass on the slide deck. You can have a look. Okay. So as I said, so we will only look at some important things. Okay. So then we can do it this more interactively. Okay. Now if I ask you, right, okay, so what are the two important constructs that you should know in Verilog? What are your answers? Okay, right. So any design, right, in a digital design, we can divide it into only two things: combinational design and a sequential design. Okay, now to do that, of course, right, So how do you really model your combinational designs and how do you really model your sequential designs? Okay. Now you tell me the what are the kind of constructs available in Verilog that you should know to kind of design your combinational circuits as well as your sequential circuits. Srikhar? Okay. So what are the two important constructs that are available in Verilog for to model or the design combinational circuits and the sequential circuits? I mean those are like different abstract type or the way you can describe your design, right? Okay, I'll just kind of help you out. So there is something called continuous statement, right? So what we call it is a continuous assigned statement. So basically we are talking about assigned statement, okay? And there is something called procedural kind of blocks, right? So what are the procedural blocks in Verilog? Always and initial, right? So why we call them a procedural blocks? Okay, right. So if you understand the difference, I mean learning other things would be really easy. Okay, good. So as I said, right, so I mean as somebody answered, so there are two procedural blocks, so initial and always, and again you see, right, initial we will not use it in a real design, right. So to initialize the signals in the test bench and all, we will use the initial block, right. So only the always block, right, so which we will use, okay, in the real designs which are synthesizable. Okay, and we will look at in a minute, right. So why we call them a procedural kind of a blocks. Okay, so here, okay, so before let us say go into the details. Okay, so now for a combinational design, right, as you mentioned, okay, so we will use what is known as continuous assignments. Okay, and for the sequential designs, so we will use maybe the always block, and of course, right, we can also use always blocks to really design a combinational circuits. Okay, before going to that, maybe if somebody is really kind of a very new to the Verilog, so if I ask you like what are the data types available in Verilog, I mean you do not have to really know everything, but at least the two important data types. Okay, so wire it's called net, right, okay, and the register, right. Okay, now I just kind of one important slide. Okay, I think I'll just move on. Yeah, so I have somewhere, yeah. Okay, so basically, right, so the net data type, okay, is the one, of course net is like a kind of a wire, maybe it connects output of one block to the input of one. Okay, and then so we have what is known as the reg data type. Okay, so this is where most of the students will confuse. Okay, now we also know a register from our digital design background. So this might be stands for a flip flop or something like that, right. But here in Verilog we have a data type called reg. Okay, we also call it as a RISC data type, but do not confuse this data type with the register in your digital design. It so happens that sometimes this register data type will exactly match the flip flop or a latch in your digital design, but it is not always. Okay, good. Sometimes the register can also be a wire. Is that clear? It is not necessary. Okay, so right. So I will again repeat, it not necessary the reg data type in Verilog always synthesized to a latch or a flip flop, which we have understanding of, it will store one bit, in general we call it as a register, right. But it not always happens that okay, reg data type will synthesize to latch or a flip flop, it can also synthesize to a wire. So we will look at these details later. Yeah, good. Okay, so one more thing. Okay, so before going to that, so this is where many of the students will confuse. Okay, as I said, right, so I am just picking up some kind of important, let us say the aspects where the students will have confusion in the interest of time. Okay, so here, so what we are trying to really show is that there is something called port connection rules. Okay. Suppose the idea is that, of course, I presume that everybody is aware of a module, okay, right. Now, it is a module is similar to your class definition in C++. Of course, right, as such if you define a class there is no use, right. So, we have to create an object out of it. So, similarly in module, let us say in Verilog, module is similar to the class and we have to create an instance out of it. So, that means we have to instantiate that block in some other, let us say kind of test bench or somewhere if you wanted to really use it. Okay. So, now, so most of the time, of course, let us say so you write, let us say one module that itself is your top level module, and then maybe you wanted to really test it or something, right. So, what you will do, you will take this module and instantiate in a test bench or something. Okay. So, now when you instantiate it in a test bench, so what I will say that, okay, so there is a top level module which is driving the inputs of your this module, okay, yes or no, okay. Now, what we are trying to really say is that there are some rules which you need to really follow, right, in such case. Now, you might have really observed that, okay, when you are declaring a module, let us say, so did you kind of declare any time the inputs as a reg, right, never, right. So, outputs could be a reg or a net. So, that is what we are trying to really depict here, that, so this is your inside the module, right. So, maybe this is your test bench, you can think of, right. So, that means whenever you declare a module, the module inputs cannot be reg, they have to be net, right. Okay. The idea is that, so if this is a kind of a module, you are trying to really connect it, right. If the input changes, so that has to really propagate it, right. It is not necessary that you have to save it, right. That is what the input means, right. Whatever it is connected to changes, that same changes it has to go propagate to inside the module. So, that is the reason the module inputs always are kind of a net type, right. Depending upon the context, okay, this output of a module, right, could be a net or could be a reg, right. But now, what that output connect to in your test bench, right. So, see here, so you need to connect to that output and just see the changes, right. It is not like that you have to save it, right. So, it is something like on a breadboard you wanted to see one of the output, right. You just simply connect a wire and just check in the oscilloscope, right. So, that means the output cannot be reg, right. So, I mean the test bench output cannot be, let us say a reg, right. It is just simply a wire, just you are watching the output, that is all. Okay. Now, what, let us say driving the input. So, now let us say there is a clock design or the counter design you have done, yeah, there is a counter design you have done, okay, there is a clock input, okay. How do you create a clock? So, maybe use some kind of always block and you will say hash clock equal to not clock, right, something like that you do it. But now, if you see, right, when you do that statement, you are assigning maybe in the clock to in the beginning to 0, right, this is a time t equal to 0, right. So, at this time the clock equal to 0, but are you assigning the clock at t equal to 1, 2, 3, 4, no, right, you are just simply saying that not clock equal to not clock after 5 time units. But what is the clock value here? Here I mean t equal to 1, 2, 3, right, okay. So, that means the one which is driving the module inputs in, for instance, a clock and all, they have to be declared as a reg. The reason is that you are assigning only once, right, and it has to save its value until the next assignment. So, then it has to be reg type. And actually, if you see, right, I mean again there is always a confusion among the students, when should I declare something as a reg, right. You have this notion where you are assigning only once and until the next assignment it has to store the value, that time definitely you have to declare that as a reg data type. And again you see, right, that reg data type will synthesize to a wire or a latch or a, let us say, flip flop, that is different. But when you are modeling, let us say designs, when you have this notion, right, you are assigning a value once and then it has to store the value until the next assignment, in between you are not assigning. that time definitely you have to declare that data type as a reg. Is that clear? Okay. So, always you should have this picture in mind, what drives what should be data type. Is that clear? Okay, good. Now, so let us go to the, I think already okay. So, as I said, right, the most kind of the use statement, and of course in a data flow modeling is this continuous assignment statement. So, as the name says, right, the continuous assignment statement, and the other one which I said, you assign once, but it will it has to store until the next assignment. Okay, that is the reason we call whatever we declare in always block as a procedural assignment. The property of the procedural assignment is that on the left hand side variables, they must be reg type. So, right, and then they will store the value until until the next assignment. Okay, but whereas if you come to the continuous assignment statement, so of course, right, the syntax is something like this. We say assign, right. Why we say it is a continuous means, right. So, this I1 and I2, they are evaluated every time, and then they are continuously driving this out. Okay. So, that is the reason we generally we will not use the continuous, but actually so the proper name would be the continuous assignment statement. We will say simply assign statement, but actually so it is a continuous assignment statement. So, idea is that the right hand side is kind of evaluated, its expression that will the result of that will really drive the left hand side continuously, right. So, now as I said, right, if it drives continuously, it cannot be reg type, it has to be net type. Is that clear? This is where most of the people struggle. So, now once you know what is a continuous assignment statement and what is a this the procedural assignment statement, everything should be clear. Yeah, okay, let us move on. So, I think, right, so this expression operand it is something similar to what Steve spoke about. So, I will just skip in the interest of the time. Okay, fine. Okay, so we always have all these reduction, bitwise and operators. Good. Okay. So, now okay. So, in a behavior modeling, this is where the procedural blocks comes into picture, and as I said, right, there are two procedural blocks. We have initial and always. So, initial we will only use it in the test benches, and of course, so always, right, we can also use it in test benches to generate the clock and all, but in a real synthesized designs so always block is used. Okay, good. So, here okay, so this is what kind of that clock design is, right. So, fine. Okay. So, okay. So, again, right, so one of the kind of a common question is that there are like two types of assignments in procedural blocks, what is known as blocking and non-blocking. You might have heard, right. Okay. So, what exactly the difference between these two? So, what we will do is that we will look at these with few examples. Okay. So, here okay, I think I do not have to really repeat, I guess, the always syntax, I guess, but if you does not know, maybe I will just reiterate. So, we have this always block, and then we have this @ symbol, okay, and then so we will give the list of signals and we call it as sensitivity list. The idea is that whenever any one of them change, so we can also put a comma, A comma, B comma, C, or A or B or C, does not matter, it is a different way of writing the code. So, the idea is that A, B, C changes, okay, A or B or C changes. So, we have to execute this whole block. Now, if somebody is not changing, what will happen to the statement? What will happen to the statement? It has to hold its value, right. So, it has to hold its value means it is a reg data type. That means, in a always block, whatever you find it on the left hand side, they have to be reg type, but in a continuous assignment statement, the left hand side will be wire. That you should always remember. Okay. Good. Now, in this case, okay, so the blocking assignments are represented using an equal sign, and later on we will see the non-blocking. So, it is a less than equal to. Okay. So, here what we have is that, okay, some two statements n1 equal to, so there is a XOR symbol A XOR B, and S equal to n1 again XOR C. So the idea here is that, so when you say it's a blocking statement, so when you see this blocking assignments, the first statements block the execution of the second. Okay, so that's the reason we will say it's a blocking. The idea here is that, so now we are kind of calculating the value of n1, right. So now the calculated value will be used in the next statement. Okay, here, so we have A XOR B, right. Okay, so now that calculated value, new value, is really used as, in the next statement, right, at that time. Okay, so I mean that's the reason we say it's a kind of a second statement is being blocked by the first statement. Until I complete the first statement, I will not go to the second. Okay, is that clear? Okay, now let's look at this one particular example. So just think about this circuit. Okay, of course, right, there should be some kind of a space here after the passage, kind of copy paste mistake, but yeah, so there is a code, so always at the passage of a clock, so right, and then we have this two statement. Okay, now actually, so my intention was I wanted to kind of swap the lower byte with the higher byte and higher byte with the lower byte. Okay, I wrote two always blocks. So think about 1 or 2 minutes and tell me what is the answer, what will happen. So my intention is I wanted to really swap the lower byte with the higher byte and higher byte with the lower byte in this word. Okay, the reason why, I mean, okay, now you tell me what will be stored in 15.8 and I mean word 7.0. Okay, now these two always statements are in the same file. Okay, so what will happen? It can run, right? I mean, again you see, right, so now we have, right, I mean this is where also kind of again the people who have a background in the sequential logic have a problem in thinking in Verilog. If you see, right, each always block, it's a parallel activity flow, right, it's independent of the other always block. Now in your answer you are thinking that the first one will execute first, right. So what is the guarantee that the second one also could execute first, right? I mean you see, right, I don't know how does the compiler results, right, it could happen that the both lower byte and higher byte could also have a lower byte or higher byte, it's unpredictable, yeah, right. So now here, I mean that's what the problem we have. Okay, it's not predictable, so we'll see the latest solution later, but that's what the issue with this code. Okay, so now, okay, so here the same code, so what we are trying to really do is that we are trying to use the blocking assignment, so non-blocking assignment. Okay, the non-blocking assignments are kind of represented with less than or equal to symbol. So here the idea is that at the passage of the clock, right, and again since these are non-blocking statement, that means both of these statements are executing in parallel. So what you are trying to do is that, okay, you are trying to really execute these two statements, you are trying to really read the word 7.0, 7:0, yeah, and then you are trying to read the higher byte. Okay, so the assignment is not happening, you are just trying to really read them, yeah, you are trying to really read them, but the assignment not happening. So now let's assume that there are the temporary variables T1 and T2, right. So this word 7. Let's say lower byte is stored in T1 and the higher byte is stored in T2, right. So both you are reading, right. So the reading is happening at a reading, or of course in this case simply reading, right. Of course if there is some expression, right, so we will evaluate the complete expression, right. So that expression evaluation is happening, and then I will store simple, think of we are storing, let's say temporarily somewhere in T1 and T2, right. Now at the passage of the clock, right, so the assignment happens. Okay, now we have the value stored in T1 and the T2, right. So we can perfectly swap, right. So that's a kind of a solution for the problem. Yeah. Okay. Now, so just to again get used to this. So here again think about this block. So draw yourself on a piece of paper what comes out of, let's say, these, let's say, code. So I will tell you later on. So whenever you see the passage of the clock, right, left hand side variables in the the code has to get a flip flop. I mean, I don't know, there are some exceptions, but the most of the time to be on safer side on record. Yeah. Okay, now that means you can think of, right. So the B and F are going to be flip flops. Okay, now what gets connected to what? So try to draw the circuit on your own. So take a minute or two and try to draw the circuit on your own. I will just check the live. Okay, good. So maybe you can just cross check. Okay. So did you get the same thing? You have a different answer. Okay. So if you think that if you have different answers, so maybe let me explain. Okay. So here at the passage of the clock, right, what you are trying to really do? You are trying to really read A and read B. But now if you look at here, right, you are trying to really assign B right here in the first statement. And you see, right, the assignment is happening at a different time step and the expression evaluation is happening at a different time step, right. So now if you think that these are the blocking statement, then you will say that, okay, oh, this C, it is the same B, right, but no, I am trying to really calculate the new value of B and then I am trying to really read the old value of, let us say, B. So that, and again as I said, right, the passage of the clock, the left hand side variable has to be flip flops. So now this is the kind of a B flip flop, right. So this output is B. I am trying to really read the value of this, right. This is my F, okay, and what is, let us say, B. So I am trying to read the value of A, and then of course, right. So in the passage of the clock we have, so the clock will get connected to the clock pins of your D flip flops. Okay. Now the same, I think somewhere I have, I guess. Okay. So this is what a kind of a swap thing we have seen. So I will just skip. Okay. So now I think with this example also we can really see the difference between the blocking and non-blocking. Okay. So now for this example, what is the difference between a, let us say, synthesized, let us say, circuit for the blocking and a non-blocking? The question is, so you are seeing, let us say, two descriptions, right, one with the blocking and another with the non-blocking. So what is your answer with respect to synthesized diagram of a blocking and synthesized diagram of a non-blocking? So the answer is that the both are going to be same. The reason here is that it is not like that, okay. So for instance, if you look at maybe the left hand side variables, right. So now something y we are calculating here, okay, the y is not really getting used in the next, let us say, any of the statements, it is like independent. So now the idea is that, so whenever we call this as a, of course, now in the previous code, right. So here, I mean, let us assume that if it is a blocking, we will see later. So now we are trying to calculate the new value here, and if it is a blocking we are trying to really use here. Whenever there is a signal interdependency, the blocking and non-blocking will differ, but in this example as I shown, right. So there is nothing like, now you are calculating the y, you are not using anywhere in the next lines, right. So whether it's a blocking or non-blocking, the circuit should be really the same. Okay, good. So whenever you have the signal interdependency, it will change. Okay, so that's what we have here. Okay, good. So here, right. So the signal interdependency is there, right. So the logic will really differ. Okay, good. Now, okay. So let's look at okay. Okay, what here? This slide, yeah. Okay. I'll come to that. Yeah, good. So let me explain you this one and then I'll come back. Okay. Right. So here, so what we are trying to really show here is that, okay, so if you look at here, right, so what are your primary inputs? A, B, C, right, okay, and you are trying to calculate the value of N1 first, okay, and then so and try to calculate the value of S. Okay, now in a blocking statements, okay, so your semantic says that you have to use the updated value of N1, yes or no? Okay, but now in a non-blocking statement, okay, so you have to use the previous value. Okay, that's what you will be able to see here. Okay, so these are your ABC. So these are your ABC. Yeah. Okay, and then so you have to calculate N1, right? So N1 is nothing but XR, right? Okay, so 0 0, it's a 0 here, right? Okay, XR of what? A and B, right? 0 0 0 0 0 0 and 0 1 1 0 1 1, right, 1 0 1 again 1 0 1 1 1 0 and 0, right. Okay, now to calculate the S, now if you look at these two, let's say, diagrams, as far as the N1 is concerned, there should not be any difference. That is the reason the N1 signal really matches in both of them. But now when it comes to the calculation of S, okay, there is a difference, right. So what you do is that you should really use the updated value of N1, right. So what is the updated value? So this new value of N1 you will use, and again what is the equation? N1 XR C, right. So you will see 0 0 0 1 0, right, 1 0 1 1 1 again 1, it's a 0 0 1 1 1 1 0, yeah, and 0 0 0, yeah, and 1 0 again 1. But now whereas here you have to use the previous value, right. Okay, right. So now let's look at, you are trying to calculate the value here. So what you will do? You use the current value of C and the previous value of N1, right. So here, right, 0 and 0, it's a 0, right. Okay, and then 1 and 1, it's a 0. Okay, 0 and let's say 1, it's a 1. Yeah, 1 and 1, it's a 0. 1 and 0, it's a 1. So 0 and 1, it's a 1, right. So you are using the previous value of N1, yes or no, right. That's what the semantic says. Okay, so now answer asked one interesting question, right. This is what exactly happens in the simulation. Okay, so answer is talking about why the circuits will differ. Anyone want to answer? No? The statements are different, but actually this is one of the kind of, I think answer observation is correct. The circuits will not differ, they will be exactly the same, but what will happen is that the same circuit also gives after synthesis the same result as the first one, right. So then what exactly you mean, right? You have a different behavior in a simulation, but after synthesis you have a behavior with respect to which is equivalent to blocking. Now what we have? We have a synthesis and simulation mismatch, yes or no? I mean to say that, so both will, let's say, will synthesize to the same logic. I will also come to the reason why it will synthesize, but now with respect to the first one, before synthesis in a simulation it is giving the expected result, after synthesis also it is giving expected result. But the second circuit in synthesis it will give you the same result as the first one, the blocking one, but in a simulation it will give the result just now we have seen. What is the reason? So basically, I mean, now in hardware what we have? We have a latch and we have a flip flop and all, right? So now if I ask you this question, in this, during this always block, with this always block, can we get a latch? Okay, the answer is no. So we will also see when we get a latch, right? So now here, if you wanted to really have a right behavior, what you should do here is that you should have N1 in here. Okay. So now in your sensitivity list, you should also change N1, right? So then it will kind of trigger immediately the logic. I mean, right? So now you will have, you know, the same kind of, you know, let's say output as expected. So there is also one more example, so which I will show you, which really kind of, you know, explains in a different way. Okay. Good. So basically the, you know, the one point I wanted to highlight is that there is a synthesis and simulation mismatch. No, we should not have that. Okay. Good. Okay. Now, I mean, this respect to the first example we have seen. So we have drawn kind of a two, let's say flip flop. So one flip flop output is going to the other one. If you look at maybe the first circuit, right? So we'll have exactly the same signal, right? So they are, you know, kind of a parallel. Now we see, right? So B is also kind of a, right? F is also A, because, you know, you are trying to really use the value of updated value of B. So that's the reason F is also connected to A, yeah, and B is also connected to A. But whereas here, so we are reading the old value of B and we are calculating the new value of B, right? So that's the reason, right? So B old value you are reading and calculating the new value, right? It should be clear now. Okay, good, fine. Okay, and again you see, right? So I think, you know, one of the Steve's explanation, you know, kind of explanations, right? So he was really trying to use only the ternary operator, right? So the ternary operator is nothing but your, you know, maybe, right? So colon and all, right? So conditional operator, and this is equivalent to our if else, and now we have a case and all those things, right? It's nothing but it's a nested if else, and everything will really kind of, you know, maybe will boil down to those, you know, multiplexer implementations. Okay, it's clear so far? Okay, good. I think so. So here, okay, I just wanted to kind of highlight few things. Okay, I mean generally, right? So we should really know how to model a flip flop and how to model a latch. So this is a kind of a flip flop code. Okay, so here what we have, this passage of the clock. I mean, in general, right? So whenever you have a passage in your always block, right? Maybe the left hand side variables will synthesize to the flip flop. Okay, good. So now here, of course, so I mean the Q and all, so maybe put synthesize to flip flop. Okay, so now what we are saying that if not reset, right? If the reset is kind of a 0, right? So right, reset equal to 0, not reset will become 1. That means if condition is true, right? So we say a Q equal to 1 tick B is 0. Okay, so that means we wanted to really reset the flip flop, and I can say it's a active low reset. Yeah, and now else Q equal to dot, right? So it's something like this here, right? So now if I ask you this question, right? So this is a clock pin. The clock pin is connected to CLK signal, D is, right? I mean connected to data, and the Q is connected to Q. Right? So now if I ask you whether it's a synchronous reset or asynchronous reset, how do you really, you know, understand that? Is it a synchronous reset or asynchronous reset? So why do you say? Right, if you see, right, that's why you should look at it. So at the passage of the clock only you are evaluating, so where you are looking the reset signal. With when the passage of the clock comes, then only you are going inside the block and then you are looking at what is the value of reset. That means reset is being looked at with respect to clock signal, synchronous, right? Asynchronous means what we should do? We simply write or, I mean in this case, right? So since I have an active low, I will say it's a negates resets, negates reset, yeah, all right, that's all. So that is asynchronous, synchronous. Okay, good. That's what I have. Okay, now I think somewhere I should also have a D latch, maybe. Okay, if not, there might be somewhere else, we'll see. Okay, I'll just skip some of these blocks. Okay, so and again I'll just talk about one of the aspect of coding the sequential circuits. Okay, good. Yeah, this is what we have. Okay, so we're talking about the latch, right? So again look at the code. Okay, so now whenever we talk about a latch, right, again think about your D latch, right? So SR and all there, but so D is the most one, right? So now for a, let's say, D latch, what is the important condition? We have to really know what is the enable pin, right? Yeah, so whenever the enable is there, the input is really captured to the output, otherwise it just have the same value. Okay, now if you look at this code, right, so do we have a passage of the clock, right? So that means there is no question of having some kind of a flip flop or something. I mean I am just trying to really kind of put together the thoughts, right? So when we have a passage of the clock or the negative of the clock, we will get maybe flip flops. So now always at the rate we do not have any passage or negates, so that option is ruled out. Okay, now what we are saying that always at the rate C changes or D changes. Okay, then this block should be executed. And now what we are saying, if C equal to 1, if C equal to 1, so maybe Q equal to D, else we are not saying anything, right? So that means, right, we can think of, right, if C, right, this is like enable, right, if the C equal to 1, then only we will copy, otherwise we have to hold the value. Now this is giving a notion that, okay, that Q, if you look at, right, in one of the condition, right, if condition is assigned, else condition is not assigned, right. So that means whenever you have this always at the rate without any passage and all, the sensitivity list, we can get a combination circuit, we can get a latch, but we never get flip flop, right. Now when do we get a, let's say, latch? We have this incomplete assignment, we are assigning the signal on if, but we are not assigning an else. So now this is giving you notes that else means store, I mean keep the same value, right. So that is where the latch comes. Is it easy now, right? So I will repeat, whenever we have a passage of the clock or negative of the clock, we should think about flip flops, right. So there is nothing like here, right. So that means there should be a combination logic or a kind of a latch. The combination logic will appear when the left hand side variable is assigned in all possible conditions. Now if you see here, if C equal to 1 you are assigning, and right, if C equal to 0 you are not saying anything. So that means your intention is that C equal to 0 means hold on, it is a latch. Is that clear? I mean I think this will help you a lot. I think again this is D flip flop code. Okay, now so this is a D flip flop with a asynchronous reset, so which we have looked at, so I will not repeat. And now I mean okay, this I think I think the issue with the okay, so Wi-Fi is gone. Yeah, I think should be better now. Yeah, okay, at least good. Yeah, now okay, now this is a D flip flop with asynchronous reset and a preset signal. Okay, now let us spend some time on this one. Okay, now as I said, right, so I think in the other class, so whenever we have this always statement and then we have this now passage, negates and all, right. I mean now in the signal name somebody written as a clock, somebody is written as a reset, right, and somebody kind of written as a preset. So don't go by any other names, but in this case, right, clock might be a clock, right, first case, right. Generally we wanted to use a meaningful names, right. So reset could be a reset and the preset could be a preset signal. I mean sometimes the reset and clear both are the same, right. So here I mean in this case I think it exactly matches, but we should really follow kind of a structure. how to really decide which is the going to the clock and all. So that I will explain, right. So now if you see here in this part of the code, right, I mean whatever the signals, right, we have if not reset. That means, so again there is a kind of a precedency, right, precedence here. So now we are giving lot of importance to, or maybe the first signal that are not reset. That means again if you see, right, so whether it is a synchronous or asynchronous, whatever we should say, you are getting into the block when any of the signals are changing, right. So that means it is asynchronous signal, right. So now if not reset, what we are trying to do, we are trying to set the Q bit to 0, right. Now else we are saying, right, else if, right. So now the second priority we are giving to preset. If the reset, first we should really set the Q output to 0, and if it is a preset, it is a active low preset, right. So that is the reason we have these bubbles here, right. So that means we should supply 0, then only it will be reset or let us say preset, right. So now the second priority is given to the preset, so we are setting the output to 1. Now else we are saying, right. So here passage of the, let us say reset we said, the negation of the reset we said, and the negation of preset we said, and else we are saying what is left out, clock, no, yes. So now, so how do we really determine the clock is something like this. The rest two are used. Now if instead of this preset I will call as A, this I will call as a B, and now I will call this as a C. Now A, B, C, right, it does not make any sense. I do not know which is a clock, which is a preset, which is a reset, right. Now I have to really look at the code, okay. So this B is used here, okay. So here A is used, okay. What is left out? Else, right. So that means this part of the block will trigger when both are not there. That should be a clock. Is that clear? Of course, right. So we will not write like this ABC code, but if somebody writes, wanted to check your understanding, you should know it, okay. So this else block only will trigger when the passage of the clock is there. That should be right. So passage of the clock, right. So Q equal to D and this one. And again you remember, always when you have the statements with respect to passage, negate, clock, so you are modeling a sequential logic, use only non-blocking, right. It's continuous assignment statement, always without any passage or anything, right. So use maybe the combination logic, use only blocking, okay. So here, so this is a flip flop with enable signal, the same explanation here, but now else came, right. So we wanted to execute this block, but we have else if, right. Now can you tell me where you are checking the enable, with respect to the clock or without respect to the clock, right? It is a synchronous enable, right. I mean you see, right, the passage of the clock only this will execute, and at the passage of the clock you are looking at the signal enable, right. So this could be your enable, and it is a flip flop with a preset, reset, and with enable pin. And now you see, right, these are the typical things which we always use, and okay, good, okay. So now I mean so this I included because of this project. Last time we had issues with modeling this sequential circuits, okay. I think it will not take much time. So I mean what kind of sequential machines we have? Only two types, right. What are those? Mealy and Moore, right. So what is the difference? Okay, right. So Moore, I think it just output depends upon your state, and Mealy is, okay. So there is always, right, if you design anything, right, so there is always one cycle delay or whatever happens. So here now I mean with this example what we will see, right, once you know the kind of a state diagram, I mean of course, right, anyway we wanted to do with a pen and paper your circuit synthesis and all, you need to have a state diagram, right. So given any problem specification, you need to really come up with a state diagram, right, and after that of course you try to synthesize with your D flip flop or T or JK or whatever, right, but of course, so we can also really write the code. So here in this, let us say example, I think I just copied from this Mary's book, and if somebody is really interested, right, wanted to really learn the digital design and all, I mean especially with the Verilog, That's one of the finest books you can find. It's a kind of very lucid explanation. And he also has all his kind of video lectures, everything online. So I think he works at University of Montana, I guess. You can just search for him, and of course, so I have the book name in the, let's say, in the reference slide. Okay, let's come back here. Okay, here, so in this example, we wanted to design a kind of a push button window controller. Okay, so somebody is giving a kind of a specification here. So this window controller will send the appropriate control signal to a motor to open or close it whenever the button is pressed. Okay, the system must keep track whether the window is open or, let's say, closed in order to send the correct signal. I mean, you see, right? So if it's open, maybe it should close, right? You should not try to again open it, right? And if it's closed, right, and then it should open it. Okay, that's what it means. So thus a state machine is needed. So the block diagram is given. Okay, so there is a kind of a button. It's a push button. Yeah. So right, so of course, right, you know the difference between a push button and a normal switch, right? So the push button, once you press, it gives a pulse and come back, and we have the switches on maybe on the basis 3 board. So as long as it's, let's say, in other position 0 and 1, it's continuously it gives 1. The push button, but it will come back. Okay, so now that's what we are giving this this push button window controller, and we are envisioning that, okay, there are 2 signals as output signal, open and a close, and now the motor we have to really kind of rotate in one of the direction. For open clockwise and the close counterclockwise, right? Okay, good. So now I mean we are again coming up with a some kind of a state diagram. Let's say there are 2 state. It could be in a closed or open. Okay, let's say we are in closed state. Okay, in a closed state, I mean nobody is pressing the button, so we can say it's a press equal to 0. We have to be in the same state, yes or no? That's an arrow is shown, and then of course, right, we don't have to do anything, right? So that means open is also 0 and close is also 0. These are 2 signals, output signal. Okay, now if we are in a closed state, somebody press a button, so we have to go to, right, open state. Okay, and then, right, what should be the signals? Open should be 1, close should be 0. Okay, again maybe it could be in the open state, so nobody is pressing any button, so press equal to 0, both signals should be 0, and then so again if you are in open state, somebody press a button, you will come to the closed state. Okay, and of course this time open should be 0 and close should be 1. As simple, right? So once you have this state diagram, right, it can be really kind of a modeled easily, and of course, right, the method which we are going to discuss, right, it doesn't matter whether you have 2 states, more states, it will be the same. Yes. Okay. So here, I mean how do you really start? Of course, you start with a module definition, output reg, open CFW, close CFW, CCW, yeah, and we have a clock and reset and the one input press, right? Okay, good. So here, okay, now when you are modeling the kind of the state machines, okay, so 2 things you should remember, right? You should really calculate the next state. So next state is a function of input and present state, right? Let's assume that, but what is the next state logic? I mean, okay, so maybe if possible we'll try to. So how do you really draw kind of a simple state machine, the block diagram or whatever, right? So we have some kind of a flip flops, right? Yes, and then multiple of them are there, right? So what you do is that you read their current state and you calculate your next state, right? Yes, and then you try to update the flip flops, right? Okay, of course, for the next states we also can give calculating the next state, inputs also will be there, right? So now the calculation of the next state really depends upon inputs also, right? And now in a Mealy machine, what will happen? Your outputs, now we calculate the next state, right? So we need to calculate the outputs, right? So now if you wanted to calculate the output in Mealy machine, output is a function of, right, the present state and the input, right? So of course in Moore machine, output is only state, and of course this will not be there. The same thing we have to really do it. That's what I want to say, right? So now when we are really kind of modeling the sequential thing, okay, right? So we need to really come up with what is known as next state logic. Now the next state logic, the way we have drawn the diagram, right, it's a pure combination logic. We will read the current state values and the input, and we will try to calculate the next state, and then whenever the positive of the clock comes or negative of the clock comes, we will simply assign. Yes or no? There is nothing really great in it actually, right? Let us assume that, so here in always in your sequential, let us say code whatever, right, you will always have what is known as this next state memory block. This is where you calculate the next state, and at the passage of the clock you just transfer to the current state. Okay, here what we are trying to really say that, okay, so we have always at the passage of the clock or the negative of the reset, of course, right. So we can assume, right, one of the state is you enter when you reset, press a reset. So we are saying that, okay, it's a active low reset and then asynchronous reset. So you always start with a kind of a, let us say, closed one. Okay, that means whenever you press, you start with a closed state. Okay, that's what we have. Okay, that means, so in the previous diagram, if I wanted to say, if it is not reset, so we are here. Okay, it's clear. Now when the reset is not there, what we should do? What is your current state? Okay, what is the current state? Next state will come, but what is the next, let's say, current state? You might have really calculated the next state already, right, based on the present input and the current state. You just at the passage of the clock, you just transfer it. That's what it's saying, right. So somewhere we calculated, let's see where we calculated this next state, and then at the passage of the clock, simply we are transferring. Now you see, right, any whether the states are 2, 3, right, something similar you find it in all the sequential machine codes. There is nothing much difference. You always calculate the next state at the passage of the clock or negative of the clock, you just transfer. This block really looks almost in same in all sequential machines, right. So we call it a state memory block, and this is only the kind of the flip flop or the sequential block. The rest are all combination blocks, right, the way we drawn, right. So the next state logic, read the current state, read the inputs, calculate the output, that's all, right. And again the next state logic, right, read the input, read the current state and calculate the next state and keep it ready so that you can assign at a next position. Okay, here and most of the time, so we will have what is known as 2 resistors. So why we have to really have a resistors? Because in always block we are going to use, so it's a current state and a next state. Okay, in this case the current state and next state, the 2 kind of variables we are using, right. Yeah, so that will represent one of your state, right. The current state could be open, current state could be closed, and the next state also could be open, or next state could be also closed. And again you see, right, so we can also say that, okay, I mean we can also really define 2 parameters. So one for closed and one for, let's say, open. So they are like defined as a 1 tick B0 and 1 tick. Suppose if you have 4 state, right, we will have a 0 0 1 0 and 1 1. Is that clear? Okay. Now as I said, right, the next state logic we have to calculate, right. The next state really depends upon only the present state and next state. Now if you see, right, when I am coding this next state logic, always let's say blocking, right, but if you look at this one, we have non-blocking. As I said, sequential thing non-blocking, combinational blocking. Okay, good. So here again you see, right, so what does the next state really depends upon? As I said, it's based on the current state or inputs. You just list all these signals in your always block, right. Okay, now you are checking the case, right? If you are in the closed state, okay, if the press equal to 1, what should happen? You should go to the open state, so right, your next state will become open, and else you are in the same state. Okay, again if you are in the open state, if somebody press a 1, you will go to the closed state, else you are in the same state, and of course, right, we have a default which is just a next closed state. Okay, so this is your next state logic, it is a pure combination. So similarly, okay, the output logic, right, output logic depends upon your again inputs and the current state. Again if you see, right, so the case statement we are depending upon the current state. If you are in closed state, if the press equal to 1, right, you should really open it, and the close of course will be 0, else both are 0. And if you are in open state, if somebody press, right, so open should be 0, open should be 0 and the close should be 1, okay, else both are 0, and we are saying the default is 0 0, that's all. Now only thing which kind of a change in Moore machine is we will not have inputs, that's all, right. Now you see, right, once you know the Mealy machine and Moore machine, right, and coding the sequential machine is very simple, and there is no other better way to code than this one, and it is easy to understand and simple. Okay, good, fine. Okay, I just wanted to mention that. And you see, like, so sometimes no, we have to really kind of write counter designs and all, right. For the counter, no, we do not have to really write the state diagram and all, but simply we can really model with a behavioral statement. So here if you see, we have this positive of clock or negative of reset, okay, and if reset we are saying the counter value equal to 0, else count equal to count plus 1, that's all, right, it just counts, okay. And again you see, right, it's a, I mean of course it's once it reaches the 15, it's again rolls back to 0. And now if you wanted to really kind of check, maybe it's a mod 10 counter only, right. So what we can do is that, okay, we can check if count reached a 10 value, of course reset means it's a 0, else first you check, right, if the count already reached 10, you initialize to again 0, right, else you just count equal to count plus 1. So but of course this should come first, okay, but if you do it again, then the results will be changing, okay. So here, okay, and we have a counter with enable pin here. So if you see here, the if the reset equal to reset is active, the count equal to 0, but now you will not count simply, right, it's not like every clock cycle you are counting, whenever the clocks, right, whenever the, at the clock edge, if you have a active enable signal, then only you will count. So in the previous one, here every passage of the clock, I mean the passage of the clock you are counting, but here in this one, right, whenever this enable is there, then only you will count, okay, that's a difference. And again you see, right, so we can also have a counter with a kind of a load also. So if enable, this should work, and of course, right, so now if the load signal is active, we wanted to load a kind of a predetermined value, otherwise so count equal to count plus 1, okay. I mean these are the typical, this, I mean you will enter, okay, good. So now this design, I mean, so one of the kind of a common task is that you have to model a register, and again you see, right, this is always kind of a confusion, right, register could be 1 bit, right, again in the context, when we talk about the processor and all, at least we will talk about 8 bit or 16 bit or 30 bit registers. So again you see, right, whenever we talk about register, so the D flip flop code should come into mind. Now if you look at here, right, it's exactly the code of D flip flop, right. The only thing is that here we have 8 of them, right. I mean you see, right, so we have the vector, I mean, right, so it could be 16 also, or 15 also, right, 0 to 15 is a 16 bit register, right. But now if you look at only this part of the code, it's exactly your flip flop code, but of course, right, here ridge out and maybe ridge in are 8 bit vectors, right. So basically it's a flip flop, okay, good. Yeah, I think that's what should be fine. And again, as I said, right, so this was a book I was really referring to, and if somebody is really interested, as I said, right, so he has all his lectures online. I'll just pass on the kind of a slides if needed. So and the lot of kind of a programming examples and all, so somebody can really look at it. Good. So maybe we can take a good break. for 10-15 minutes and then okay. So if not, right, so we can just continue with the lecture until your refreshment is available. So here onwards, so you should work more, I will talk less. Okay. So it's better, I think, just we'll continue until the tea is available. Okay. So as I said, right, so okay. Okay. So far maybe I just try to give a kind of some glimpse of the Verilog itself and kind of a common misconceptions or misunderstanding. Okay. How do we really understand such nitty-gritties? So what we'll do now, I mean, writing the code is one part, right, and this is where it's kind of there are a lot of not much material available, and again as I said, right, so we'll also kind of formulate some rules by which we can really understand easily. Okay, good. So again, so we call our synthesis. So what is the synthesis general meaning, right? General English meaning, right? So transforming from one form to the other, right? So now in a Verilog, let's say domain, right, we have statements. So now after synthesis, what we have to get? We have to get some kind of a flip flop, latches, and all those things, right? So now of course there are some tools which does that. So we are, let's say, transforming from one form to the other. Now, so of course, right, the synthesis really depends upon whether it's a ASIC synthesis or FPGA synthesis, right? Okay. So now, I mean, in FPGA synthesis, in FPGA what we have, LUTs and all, right? So maybe your synthesizer at least only consists of your LUTs, but in ASIC synthesis we will have AND gates, OR gate, multiplexer, and again depends upon what you have in the library. It's not necessary that, if you think of a full adder, right, in my library I have 1-bit full adder, I don't need anything, I'll just simply instantiate that 1-bit full adder. But if I do not have a full adder, I have a half adder, I will build the full adder using 2 half adders. Suppose in my library I don't have 2 half adder circuit, what I have to do is that I have to build my half adders using maybe XOR gates. Okay, let's assume that again XOR gates are not available in my library, I have only simple AND gates, OR gates, right? Even the XOR gates tries to be built using that components. Again you really see, right, the synthesis really output depends upon what you give as an input, right? If you give input with respect to I mean the standard library, right, so standard cell library you will give, and it all depends upon what the standard cell library contain, the output. If you have all the gates, like generally we see, right, the multiplexers. So generally the multiplexer also will be given as a simple kind of a standard cell. So whenever we need a multiplexer, we will not implement with inverters, AND gate and OR gate, we simply use the multiplexer, it's much more efficient in terms of area and all. Okay, good. So maybe after this let's say statement we'll take a break. Okay, so now I am just trying to ask myself, what are the kind of a value holders for hardware modeling in Verilog, right? So now here in a Verilog, or I mean of course in the hardware, right, of course in the Verilog world what I have is a net and reg predominantly, right, but in a real hardware world what I have a wire, I have a flip flop and a latch, right. Now the question is, whatever you write in Verilog, that should really come and match to any of the things. Now I am making one statement that here a variable in Verilog HDL can be either of net or net type or reg type, right. So that means these two has to really map to these things. Now in the last statement what I am trying to say that if there is a net data type, definitely it will become a wire. Whatever is very simple, a net data type has to become a wire, but now the reg data type, depending on the context, okay, it can become a wire, it can become a latch, it can become a flop. So just to conclude maybe this slide, in a hardware we have a net, we have a latch and a flip flop, but on the Verilog side we have only net and reg. That means these two variables has to really map to these things, and the statement what I am saying that if it is a net, it becomes net only, it is a wire, but if it edge could become also a net, edge could also become a latch, edge could also become a flip flop, and then we'll look at following lectures, I mean, right, what are the conditions or in which conditions it will happen. Okay, good. So let's pause for a break. Yeah, yeah. And this is where I said, right, so you should work more compared to me. So keep your pen and papers ready. Okay. Rohit, let's get back. Okay, good. So again, what I'll try to do is that, I do have a couple of slides, but again, so we'll again, look at few important things so that, you get the main kind of, the ideas, and the rest, I just pass on the slides, you can just have a look. Good. So here, so let's look at this part of the code. Again, from now onwards, we'll just look at the code and think about what comes out. That's the idea, right? So let's look at this part of the code. Okay. So now we have always block, right? There's nothing like passage or anything, right? So only option at the latch or these things, right? But again, latch means, as I said, right? If something should be there, that is also not there. Huh? Check. Huh? Okay, should be fine. Okay. So here, so the importance of this example is that, so here we have this TRQ, right? And of course, we have a blocking statement and all, but now this TRQ is really used here. Okay, now if you think that, as I said, all the left hand side variables, of course, right, in a always block has to be reg type, but now if you say this SQP or TRQ, right, so they will both really kind of become a reg type, and now the circuit will something look like this TRQ, right. So now we see, right, there is nothing like a kind of a register or something came out. So again, as I said, right, if you are comfortable with the always block for even modeling the combination logic, use only always block, and of course, right, in always block we have this advanced constructs, right, if else case and all, it makes much more sense. And otherwise, we have to use only the ternary operators and the continuous assignment statement for modeling the combination. Right, good. So now again think about this circuit, and again this points to what answer Riley pointed out earlier. It's a blocking, right? So now you are reading TRQ even before you calculate. So what is the value of TRQ I should use? Maybe the past value, right? Okay, now the past value means I should either it should come from a flip flop or a latch, right? Is there any question of coming a flip flop here? Yes or no? No, right? Because we don't have any pass edge or any gates. So there could be a latch. But again, you wanted to assign the TRQ, right? The TRQ could be a latch. But again, latch means there should be some enable condition, right? And that means that the TRQ should be assigned in one of the if condition, else condition would have been kind of left out. It's not the case, right? Okay, this is again result in a kind of a synthesis and simulation mismatch. It should be some kind of a TRQ here should be added, otherwise it will not work. Yeah. So now if you wanted to have a, and now if that is the case, so I think the previous circuit I think should also be the same. So the behavior will be the same. Yeah. That is the reason we should be a bit careful. We should not have synthesis and simulation mismatch. Yeah. Good. Okay. Now, so work out on this example on a pen and paper based on what we discussed. Just you don't have to write the code or anything. Just look at the code and try to draw the diagram. Later on I will pass on the thing to you. So is there a question of flip flop or something? No, right? Okay, now is there any question of let's say latch? Yes, right? Okay. So what is going to be latch? Again you see this is where okay, let's assume okay this is your D flip flop now. So this is a D input, this is a Q input and this is enable pin. Synthesis means what? We have to come up with a D logic. What should be connected to D? What should be connected to enable? What should be connected to Q, right? Okay, now in this case, right, what should be connected to D? What should be connected to enable? Think in this way, right? What should be connected to enable? If not SAT, right? Right, of course, so I will say it's a something like this, right? If this is true, this is a SAT signal, then only it will work, and then in that case where should I really write fox? I mean, doesn't make sense fox and ant, but that's what the book has. Yeah. Anyways, where should I write fox and where should I write ant? Very good, right? So this is your output, right? And this is your input. Okay, and then there is something called S out, right? Where I should write? I mean, of course, if you have a Q bar, either way, of course, you can also take something like this, yeah, and then this is your S out. Yeah, if the Q bar is available, just take it from there. Yeah, of course, it's overlap with the other one. Okay, good. Yeah. Okay, fine. Okay. So now again, so when we have the continuous assignment statement, right? So here if you see, right, this assign, this kind of a start out equal to the start in. Yeah. So basically, right, so always remember, whether it's always or the continuous block, we have to evaluate the right hand side. Okay. In the right hand side, we have an expression. In this case, the expression could be simple, right? It's a not start in, right? That has to go to the left side. And again, as I said, right, whenever you have this continuous assignment statement, the start out should be really wire, and of course, right, so it should be really driven by whatever the expression you have. It's a not side. Okay, good. Now when it comes to the procedural assignment side, we had a blocking and non-blocking. So we talked enough. So what you do is that, let's look at some examples. Maybe first I'll come here and then we'll go back. Okay, think about this circuit. So draw me what comes out. So draw me the circuit, what comes out of this one. So maybe in this interest of time, I mean, it's very simple. So of course here, if you see here, always there is a non-blocking, right? Of course, I mean, you don't get confused. There's nothing as a positive clock or anything is there. There's no flip flop, right? And there's only one statement. It doesn't matter whether it's a blocking or non-blocking, but I would say that if it is combination, use only this one. Okay. So now, as I said, so there's no flip flop. There's no latch also. It's a simple reg A and reg mask. We should really AND, but since reg A and mask are, let's say, 4 bit, and we'll get maybe 4 AND gates, right? Right. Good. Now think about this circuit. This one will be flip flop, right? Okay. Now whenever I say it's a flip flop, again, what are the inputs we have? We have a D input, we have a clock input, and we have Q output. Now what should get connected to what? Very good. Okay, very good, right? So it something like this, right? So D flip flop. So the clock is connected to, of course, this CLK signal, right? And of course, right, each bit is connected to, of course, this reg A3 mask 3, right? Of course, for each bit we have one flip flop, right? So we have 4 bits, we have a 4 flip flop. Agreed? Okay. Now, so the other one which I said right here. Okay. So look at this, let's say, circuit, and again you see, right, what we need to know is only simple, kind of a Boolean minimization, and we need to know only the Karnaugh maps or whatever, nothing else we need. Okay, we'll see that. Okay. So look at this circuit. So what this circuit is trying to do, I mean, whenever there is a change in preset changes, so count equal to preset plus 1. So basically it's an adder, right? Yes or no? But now there is one difference. Of course, we can say it's incremental, and now instead of preset plus something is there which is a variable. So here we are adding only one, right? What we can really do is that we can really optimize the circuit. Instead of this preset, there is one signal. I mean, I don't know, XR or whatever. Again, maybe it's a 2-bit signals or whatever. So then we have to synthesize a complete different, full kind of adder. But since we are adding only one, what we can really do is that we can really minimize the logic. So how do we really do that? And again, so I mean it will take some time, but you see, right, so we have a 0, right, preset could be 0, so plus 1 means what, 1, right, so 0 0 1, right, and again is 0 0 1 means we added 1, right, so we have 0 0 1 0, right. So now what you do is that you draw the kind of complete, let's say, the truth table, and you get the equation for C out 0, C out 1 2 3, draw the diagram. So that itself is your synthesized diagram. I mean, you try to do it at home and you will get these equations, and you can check with what we have here. And again, as I said, right, so the diagram which you have may not really match with this one, but you look at the expressions here, because as I said in the book, right, he used what is known as this AOA gates, OA gates, that's what the library has it, but doesn't matter, right. As I said, the synthesis output really depends upon what you give as input. I mean, in this library he has this OA gates, AOA gates, and or invert and all. I presume answer is converted, and let's say talked about these things in the digital CMOS VLSI design, right. So if you look at, right, so this AND gate we have, right, A B bar, right, OR gate, right, so we have A plus B bar, right. So we have see, right, so OR, we are trying to do the OR of the signals, and then, right, and here we are trying to do the AND of the signals, and then negate. So this which way you have pushed? Could be, no, I mean, see, we can really optimize, right. So you are adding only one, right. So it's not like you are adding some kind of a generalized value, right, 2 3 or something, right. So here you are adding only one. It's not like you are adding, let's say, 2 or 3 which can really variable. So here, right, so then we can really optimize. So I think sometime I think Anne answer asked, it's one question in one of the presentation, right. If you are multiplying by only 2, but now the multiplies A plus, let's say A multiplied by 2, right, we can just optimize the circuit, but A multiplied by B, I mean B value could be anything, right, we cannot optimize unless we know the value of B, right. So that's the same thing here, okay, good. That's fine. So there are some more things, okay, the logical operators, right, the logical operators exactly translate to the gates, so we don't have to talk about that. When you have these arithmetic circuits, right, we have signed and unsigned operation, right. So I mean, in arithmetic case, right, signed or unsigned doesn't matter anything, right, I mean doesn't make any sense, right. Only thing is that it's the same adder, but the inputs are really represented in signed and let's say 2's complement form. Yeah, good. So let's skip those slides. Okay, relation, equality, okay, fine, okay, this is also fine, okay. I mean, okay, what we'll do, okay, so there is a conditional expressions, right, if and else, okay. So again, take a minute or two and think about what comes out of this logic. So try to really draw the diagram with respect to the signals, and again, as I said, right, all the operators, logical operators, will result in a kind of a translation to gates. Right, so here you need to calculate the XOR of this one if this condition is true, else this one. So basically, of course, it's a kind of a multiplexer, where to the one input this goes, 0 input this goes, yeah, and of course, right, the condition is not reset, and of course the diagram might look different, but it's exactly what we talked about, something like this, right. The condition itself is not reset. We have 1 and 0, 1 is connected to this one and 0 is connected to this logic, right. Okay, so that's also fine, okay, okay. Okay, now yes, right, hardware you have no, here if you see, right, on the hardware you have to perform this one and perform this one, and then it's a combination logic, right? It's again, you know, the left hand side has to really drive the right hand side always. So, right, so I always execute, right, and of course it based on the register signal I will select. But again, do you have a control over the reset? If you know already that reset is a constant value, then I don't need this expression, right? But here the question is that you do not have a control of reset. Reset could be input, right? It's someone else gives you. But already if you know the reset value, we don't need this expression, right? Either we can just compute the either true value or false value, that's all. But you see, right, we do not know what value we need, right, and it all depends upon the reset. Yes. I mean, again, you know, maybe we have to modify the code. Okay, and I understand what you're trying to say, that it's kind of again a latch, you, right? If the reset equal there, then only you evaluate and pass it on. So then, you know, can be done, but again you see, right, it's a pure combination logic. So okay, good. Okay, now there are a few important things we'll do. Okay, so here again, can you think of a kind of a logic diagram for this one? Very good. Okay, now so for instance A and B, right? So what is the way is saying is that, I mean, you see, think in terms of not gates but bit higher components, right? So this could be a select signal, right? So maybe I will giving this A and B to some kind of a comparator, and now whether this A greater than B, that will come as input. It could be true, it could be false. If it's true, I will assign A here. If it's false, I will assign B, and this is Z. Okay, now whatever you have is exactly the same logic. Okay, and now later on you just try to really derive the equation and just try to check it will match. Okay, good. Right. So now here again something simple, right? Something similar, but in this case we have this is a control, right? It's a true and false. What is my output? Z. Input side I have this A and B. Here I have A or B, right? Yeah, good. Okay, again, you know, so this looks a bit different, but it's exactly the same. You can cross verify. Okay, now we can do this exercise. Okay, now again, so again look at the code, think about, you know, what is the possible outcome of this circuit, and this time let's kind of, you know, maybe solve it. So now here, is there a question of let's say flip flop? No, right? Since we don't have a passage or anything in the always, but there is a if, right? Okay, good. How many latches? The first question. Look at now what is the Z value, right? 3 latches, right? So now that means there will be 3 latches, and what is the latch enable condition? 5, right? 5 is 1 bit. That means you can expect in your circuit there will be 3 latches. Okay, all latches input, let's say enable pin connected to 5, right? You already know, and one latch output is Z0, Z within bracket 0, right? Z1 and another one, and Z2. Of course, right, just please watch out. So here we have used is a little Indian notation or big Indian notation? Big Indian, right? Normally, right, we will write 1:0, right? But we wrote it. Let's just watch it out. Okay, otherwise nothing. Right? Okay. Now, how do I really derive the logic for Z0, Z1, Z2? So please think about what are the inputs, right? What are the inputs? Ones, right? So what is the ones value? 0, 1. I mean the bit size is 0 and 1, right? What are the values it can take? I mean 0, 0, 0, 1, 1, 0, 1, 1, right? Now once you add 1, what will be the output? I mean is Z is the output, and of course Z is one more bit extra, right? 0, 1, 2, right? That means what you should do now? write the truth table with ones as input, assume that you are adding 1 and come up with a truth table for Z0, Z1, Z2, right. And now in the output table what do you have? Z0 we have, Z1 we have, Z2 we have. So please tell me the expressions, that is all. Vishwajit. So here I am trying to just tell you that, okay, I mean we think that the synthesis is something different, we do not understand the circuit or something. I am just trying to really prove that if you know the truth tables and a little bit of the K maps and the Boolean expressions, minimization, we can get exactly all the circuits we want. Okay, good. I will just I do not remember where I have, but in the morning I was trying to open. So this is what I was trying to really refer that, okay. So we have ones 0 and ones 1, right, those are the inputs, right. And now in the output side we have a Z0, Z1, Z2, again as I said, right, do not confuse with the little Indian and big Indian notation, right. So we can have a 0, 0, 0, 1, 1, 0 and 1, 1, once you add what will be the values, right, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1 and 1, 0, 0. So now what I should do, if I wanted to get an expression for Z2, I mean, right, I will make a Karnaugh map, right. Yes or no, right, and then get an expression for Z2, Z1 and Z0, yes or no. So we should be able to get an expression, right. I mean we can do it, but but the interest of time I am not doing it, yeah. So once you get these expressions, right, we just need to really draw the diagram, right. Okay, as we said, so we will have a 3 latches, and again this CK is a enable input, it is connected to 5, so it is in the next page, okay. What is the Z0? So Z0 nothing but it is a 1 0 and 1 1. So where do I get 1 0 and 1 1? Those are the input, right, okay. So we have this 1 0 and 1 1, and of course it is a simple AND gate, right, we have an AND gate, and similarly Z1 I derive the logic and connect here, and for the Z2 also it is just 1 1 bar, I will just connect it. I think I have in the next slide here, yeah. And now we see, right, all the enables are connected to the 5, right. Again you see, right, at a moment it looks like a bit complicated, but once you know the K maps and all, it is easy to get. Good. So there are a few other things, okay. Now look at this code, there is some issue with this code, I mean it is fine, it works, right, but there is some issue with this code, and again it is concerned with the students and grades, right. So what is the issue? Okay, no else statement, right, that means we will get a latch, okay. So but the problem is that if the marks are, let us say, okay, one student got 2 marks, what should be the grade, right. So now the next student got, let us say 10 marks, or let us say 9 marks, sorry, pass, right, okay. So now next student got 2 marks, what is the answer? Fail, right, and the next student got this time 11. See how come if the 11 student 11 marks means fail, I mean the circuit is, I mean, logically fine, it's same, right, but again you see, right, when you, let us say, if you are asked to do such thing, right, when now it says that, because if you say 11, I mean it all depends upon what was the previous state. If the previous state was, let us say, the 7, I mean then it could have been, let us say, pass, and the 11 also will say pass, maybe instead of excellent or something like that, right. So basically, right, so here definitely, right, we should have an else statement, right, and then model the circuit. Of course here synthesis everything we can do, but it is not about that, right. So here you can also think about logically what should be the right way to model, right. So now if you do model something like this, so we will have issues, that is what I want to highlight. Okay, good. What? Which one? Internal resistor? Okay, okay. So of course, I mean, you know, we can really combine this, right. So now we just simply said output, right, okay, but as I said the left hand side of the variable should be reg, right. Right. See, in always statement the left hand side of the variable should be always a reg, right. So that is the reason we declared this one, otherwise, you know, we can also simply write output and reg, that is fine, and then you combine this. Okay, good, fine, okay. Okay. Now I think I will skip this case statement. Again in the case statement, right, it is a nested if else, right, if else, if else, if else, if will check, and again in any one of the branch if you miss, it is going to be a latch, and if you have a complete list, it will be combination logic. Okay, I will just skip. Okay. Okay. So now I think this is what it's mean. I mean, this is okay. The simple example are there. Okay. So again think about, let us say, this circuit and try to draw the kind of a circuit which you get it. It's very simple, I guess. So try yourself. Whenever the clock A changes or current state changes, you enter into it, and if clock A, the current state, right. Again it's a latch. What should be the enable signal? Clock A, and of course, right, next state 0 is connected to the current state 0. I mean 2 to 2, 1 to 1, and 3 to 3. So this will be something like this. Yeah. Okay. Good. So now this is an interesting part. We will spend definitely some time here. Okay. There are 3 bits, right? I mean 0 to 3, total 4 bits. 0 is connected to 0, 1 is connected to 1, 2 is connected to 2. Yeah. Yes, but now, I mean, of course, right. So now at that, so now if you see, right, okay, yeah, I understood your question. So for instance, current state change, so we should enter, right. Okay, now then you are anyway you are checking clock A, right. Yeah, and if clock A change, right, if the clock A change, we should also enter the block, right. Again think about the latch functionality, right. Right, if the input change, if the enable is active, we should send the out, right. If the if enable got changed, right, if enable got changed, again we should go into the loop and we should, you know, change the output. But again you see, right, then I think there's one thing which I forgot to tell you, right. In always block, when you are writing, you know, the kind of, you know, the modeling the combination logic and all, right, we should list out all the signals which are on the right hand side, right. So yeah, so then it will correctly capture the behavior. If any of the input changes, it will just trigger. Now if you see, right, no, again you see, right, I mean as I said, right, in the hardware I have only wire, I have a latch, and I have a flip flop. Now what you are saying that you will not put this one, right, but again you see, right, in your simulation what will happen, you will get something, but hardware, you know, somehow it gets the same thing. Hardware just generate the warning and most probably will get the same circuit, but the problem is that you will have a one behavior in simulation and one behavior in synthesis. Okay, good. Okay. Now, I mean we have latches, right. Latch can also have kind of a reset pin, the preset pin, right, and we can also have enable. Now in this, let us say, kind of, you know, this let us say part of the circuit, what we have is kind of we have something called reset or set R and a clock X R or current state. There are like multiple things. Now if you look at the code, right, what we are saying, if not reset, so we should say that the next state equal to 12, else if next state equal to let us say 5, and again else if clock X next state equal to current state and else is not mentioned. So now first of all, because it looks like maybe a flip flop or something, right, but again as I said, there is nothing like a passage or anything, it cannot be a flop, it could be a latch because one else block is missing. Now again if you see, right, so we have, let us say we have a priority, right, again if you look at the code, right, first we are checking if block and then else block and then again we have else block, right. So now we have some kind of a priority, and now you enter into this loop whenever anything changes, right. So that means reset is also kind of a asynchronous, and I mean set also is an asynchronous. If any of those changes, your output should really change, right. Is it clear? Fine. Okay. Now how do we really get the logic correctly? So now what we are thinking about, we were thinking about a D flip flop, D latch, we have a D input Q and we have NF, and now we are thinking about, we have a kind of a preset pin and we have kind of a reset pin. Again the preset could be active high, it could be active low, or the reset could be active high, active low. Again you see, right, whatever the circuit comes out, it depends upon what kind of cells I have, right. Is that clear so far? Okay. Now how do we really go about designing this circuit? I know that next state is what, 4-bit signal, right. I only know that definitely there will be 4 latches, right, there will be 4 latches. Okay. Now how do I get, let us say, first latch? So how do I get my first latch? Okay. Okay. Now let us say, okay, I am working on the next state 0 or whatever. Okay. Let us say this is next state 0, I will just kind of abbreviate with the next state 0, I am working for this one. Okay. I know that, right. So this is a D and there is a Q, right, and then there is a enable pin, right. And now, so since it's there is a asynchronous pins are there, right, asynchronous signals are there. So now I should also have maybe a kind of a flip flop with maybe asynchronous pins. Okay. So now if I look at, right, so in the the solution, so I have, let us say, first of all, okay, next state 0, right, let us try to stick with this one. So we have a CDN, right. So CD stands for the clear data, clear pin, and N stands for it's a active low. So now what he is trying to really say that, so we have this CDN pin which is active low, that is what is synthesized. So let us try to stick to that, exactly the same thing. Yeah. Okay. Now as I said, synthesis means what, we have to derive the logic for the D input, we have to derive the logic for enable input, and we have to of course connect, let us say, Q, right, to proper signal. So how do we really get? Any ideas how do we really solve it? Okay. Again as I said, right, so we just need to know about truth table, nothing else. Okay. Now if I say that I have a reset, right, and I have a set and I have clock X, right. Okay. I am now simplifying for maybe the next state 0, right. So this is my output, these are my inputs. Okay. Now so what we said, it's a 12, right. So 12 means what, 1 1 0, right. So 5 means 0 1 0 1. So now I am talking about this first bits, right, 0 and 1. Okay. Now if you look at the code, right, it's a not reset. Not reset means reset should be 0, right. If it's 0, what will happen? Irrespective of this one, na, what is my output? 0, na, right. And now reset is 1 only, then I will go to the next signals, because if is a higher priority, right, if reset, right, if as long as 0, then I do not even look at the other signals, yeah. So now if I want to go to the next one, reset should be 1. After reset, if the set equal to 0, right, if the set equal to 0, I do not even look at the clock X, I do not even look, right, it does not matter, right, like the dash means now it could be 0, 1, does not matter, right, but here in this case the reset should be 1 and the set should be 0, and again the clock X could be 0, 1, does not matter. So what will be the output? It is a 1, no? Yes, okay. Now if the reset equal to 1, set equal to 1, and then if the clock X equal to 0, what will happen? What will happen? The next state is equal to current state 0, yes or no? Yes or no? Okay, now, yeah, understood, right? Okay, now look at the circuit. So here this output is 0, right? What actually this CDN pin will do? If you give a proper active signal to that, it will set the output to, it will set the output to 0, yes or no? Okay, now in the solution he is using only the flip flop with the CDN pin, that means his library only has the latch with the active low clear pin. So then what we need to do is that we need to really redirect the input, let us say truth table, appropriately to the appropriate pins, right. So now let us say if I ask you this question, if I give this CDN, let us say, right, that input 0, what will happen? If I give the CDN input 0, what will happen? I mean according to the truth table, what will happen? Output 0, no? Yes or no? Because it is a CD pin, it is an active low pin, that means if you give 0, then only it is active and then output should be set to 0. Now according to the truth table, now what signal I should connect it to? Right? If I simply connect what? Reset, right? Yes. So now the CDN, simply if I connect the reset, what will happen? Just, I mean, let us connect it and check it, right? There is no harm, right? Reset equal to 0, what will happen? 1, right? Reset equal to 0, what will happen? Output is set to 0. I mean, it is satisfying the truth table, right? Okay, good, right? So since we have only CDN pin, that means in the output, so this, let us say, right, output is set to 0, and now we connected this one, and that means, okay, we have completed this entry, right? Yes. Now what is left with? We left with these 2 entries, okay, we left with these 2 entries. In these 2 entries, what we should do? We have to make the latch open. First of all, if you wanted to send the output, right, to the queue, what we should do? We should make the latch open. So latch open means we have to derive first, enable condition, right. So what is the enable condition? Now looking, I mean, look at the truth table and tell me what is the enable condition. So in enable condition means in these 2 cases I should make the flop, let's say the latch open. You tell me what is there, what do you see there? Some kind of expression can you come up with? I mean, of course we can really draw the truth table and derive it, but I just wanted to save some time. This enable condition, right? Reset should be what, like 0 or 1, right? So can I say it is a compulsory reset, right? Now its reset should be 1 and set should be 0, right? I mean, of course, right? Now I wanted to say that set should be 0 means not set, no? Because I wanted to make it 1, right? Enable pin is what? Active low or active high? Active high. So that means I should supply 1, right? Right? So I should take not set. Okay. Then other condition, again reset should be 1, this one, and and other condition, I mean I can neglect, right? So not clock x, right? So right, reset should be definitely 1, right, and of course I can leave this, but this should be 0, right. So that means not clock x, right. So now what I can do is that just connect this logic to the enable pin, right. That means in these two conditions you are opening the latch. Okay, now what is the D input? What is the D input? Huh? Now you should send 1 once, right. So of course current state we can send directly, right, but we should also send, so we should also send 1, right. So when you send 1, what is the D logic, right. So definitely CS 0, right, okay, and we should send 1 when, right, if set, but when is the condition, reset should be 1 set bar, okay, and then that time you are sending 1, it's a 1, yes, okay, now yeah, got it, right. So basically again as I said, right, the problem looks bit complicated, right, but when you start really doing it, right, it's simple. Again you just need to ask yourself, what is the, when should I really open the latch? Okay, now for instance it could happen that there was a kind of a latch with a preset pin which is active high, right, we will just take this condition, right, yes or no, right. So now since we wanted to match the solution which is given, we are just taking this one. Now in this case for instance we have active high, sorry, active low, clear, right. So what is the guarantee that we have a latch with CDN? So now I have a latch with only CD signal, it's active high. What should I do now? Just negate the logic, right. See, instead of connecting the reset, you connect not reset. Yeah, is that clear? Okay. So do you want to try for the next, let's say bit CS1 on your own? So maybe I'll just zoom in this part of the circuit. I mean again I'll just show the solution, but at least I want you to kind of think through. And again, right, so maybe I am trying to really come up the expression by just looking at the table, but if somebody comes confused, right, you just draw the truth table, get the output equation, everything you will get exactly the same. You don't have to really do that. Just give me a second. And again, as I said, right, I wanted to match the solution which is given in the book so that I can cross check. So now for the current, let's say this the next state one. So if you look at the solution, he used a kind of a latch with a CD pin, right? It's not a CDN pin, just wanted to know really, just right. So now if it is CD pin, of course, now again if you look at, right, it's a 12, right, 110 and 0101, right. So in both cases connected to, I mean it's a reset or a, I mean not reset or a set, it's a both 00, right. So that's what we have. So now what he's trying to really do is that, okay, this both cases I will really map it to the CD pin, but now the CD pin is active high pin, right, it's not a active low pin. So now in these two cases, if I take this condition like, okay, now if you look at, right, so we have reset bar plus set bar, right. So what is the condition? Reset bar or plus set bar. So what will happen? Either one of them is 0, right. I mean for instance, so one of them is 0, reset bar will become 1 or the set bar will become 1, right, and then I can connect it to directly the CD, right. So now assume that instead of the CD we have a CD pin, CDN pin. If it is active low, what we should do? We should simply take reset and set, right. If any one of them is 0, the output is 0, right, and one case only will go to the next one, right. So 1 case means this is a 1 actually, right. So in this way, right, so we can really, I mean, solve all these questions, okay. So just again, I just wanted to really emphasize that, okay, I mean the whatever the synthesis tool is trying to really do is not really magic, right. With a pen and paper, what we are trying to really do, it's doing the same thing, but maybe it's automated, right. And of course, as I said, right, maybe with a pen and paper we are a bit limited, but again, so tools, algorithms and all, we can do much better. But this is a principle. It's also try to derive this kind of expressions, try to simplify, come up with the equation, okay. And now onwards you should really not only think about writing the code, and if you write the code, what will come out, that you should think, okay, good. So if somebody needed, so I just kind of pass on all these things. So okay, good. So let's move on. Okay, again maybe here it's wanted to emphasize again. So CD, CDN, okay. So you see, right, one of the let's say latch he used only the PD pin, right. So 1100, right. So 0101. So now in this case, right, we have 11. For that one he is used only the PD pin. So that you will find it in the solution. But again, the same procedure we have to do. Okay, good. Now look at this code. I think the code, I think I misplaced. Okay. So okay, the code is missing, but anyway, it's fine. Okay. So let's come to the flip flops. Okay. So as I said, I mean this is what the slide summarizes. Let's not read the slide, but let's try to kind of make a statement. So whenever you have a always statement and we have to look for an event, what is that event? It's a positive edge of the clock or the negative edge of the clock. So when we have this kind of a edge event, then only you will get a flip flop. Okay, that's our standard. Yeah. So this we call it as a clocked always statement or something. Okay, now so try to kind of draw the logic for here in your own terms, right. So that this kind of the diagram which I have drawn, it looks really different. So try to think about this code and try to draw your own diagram. You can think of, right. So there is a flip flop with only D input, clock input, and a Q output. So basically we can think of, right, I mean we'll see what is exactly this means, but okay, we can think of that, okay, we have a D flip flop, right. So D, okay, I mean, so let's assume that, okay, we have a only positive trigger, right, I mean, right. So then we should really connect with the negate, yeah, but if you have a negate triggered flip flop, you can simply connect the clock, yes. So CL was CK, right, and now the D input, right, of course if you see, right, if there is a control signal, right, it's like multiplexer with a control, I'll use the control, if it is a 1, it's a A, it's a B, and then this will go here, and then this Q is connected to Z, okay. Now, and what is this is that the library which he is using, right, it has some inbuilt mux, that's all, and now the mux, one input should be connected to the D1, 0th input connected to be 0, and then your select signal should be connected to the SD. So now you can think of this mux is really residing in the flip flop. He has that one, doesn't matter, yeah. Okay, it's the same thing. Okay, good. Now again, right, so here, I mean, I just want to again know, so here again, since we have a passage of clock, so this will definitely counter will be a flip flop, but again the counter you are adding, right, but you are not adding a generalized value, it's a plus 1, right, again the same holds true, that since you are adding 1, we can really optimize this logic and connect it to the counter. So let's not do it, yeah, there are few other things, okay, good. Now, okay, can we spend some time on this? Again think about how you are really going to, let's say, design it. Okay, this is a up down counter, this is an up down counter, yeah. So whenever the control signal equal to 1, you are doing up counter, and whenever the signal equal to 0, you are doing an up, let's say, down counter. So now how do I really kind of come up with a circuit for this one? So try for 5 minutes or so. Again, the counter is not a big counter, right? It's just only 2-bit counter, 0001 1011. And whether it's a chisel or whether it's a TL-Verilog, whether it's a anything, ultimately you have to end up in a Verilog. Of course, the code you are not writing, right? The TL-Verilog also translate to your Verilog, right? Or chisel also it's a Verilog, right? And again you see, right? So having the knowledge of how the tools works, the knowledge of how synthesis will happen might really help you to debug your designs. Again you see, think about, right, so control is 1-bit input, counter could be 2-bit input, right, current, right. So now 0001 1011, right, if the control equal to 0, you down count from current state to the next state, and if the control input equal to 1, you will up count. So then you can come up with a truth table and derive the equations, right. Yeah, I know, I just wanted to really bring out the complete idea. Okay, if you see, right, the simple method could be this, what I just again I say, right. So control is a 1 bit input, it could be 0, and then we have to change the current state outputs, right. It could be 0 0, it could be 0 1, it could be 1 0 and 1 1. So when it's 0, right, what is it? It's a down counter, right. 0 0 means what is the next state will be 1 1, right, and 0 1 is a current state, is a down counter means 0 0, right. So if it is a 1 0, it is 0 1, if it is a 1 1, it is 0 1 0, and then so control could be 1, and again the current state I just enumerate and then I will derive it. So now I will get, let us say, the next state 1 equation, next state 0 equation, right, and now I will just simply write the flip flops, right. Okay, maybe this is my next state 0, the left side one is the next state 1. So if you look at maybe the next state 0 equation, it simply says 0, right. The current 0 means from the negative input I am just taking, connecting it, right. So maybe the next state 1 equation, right, it's a bit complicated. It's now if you look at maybe this part of the equation, right, right, it's with a control bar, and this part of the equation, the last two terms, it's with a control, right. So I am just simply using again a multiplexer, right, and then just generating the first term and the second term and just connecting it, right. Okay, now if you look at, let us say, the book, right, the actual solution, he is using the kind of the flip flop with a D1 D0 and all, but again so we could also really do that. Okay, so here just what I did was, right, to just match the solution which is given, right. So he is using the flip flop with D1 D0 pins. Okay, now when the control equal to 0, right, so I will not change any D1 pins, right, I will only change the D0 pins, yeah, and when the control equal to 1, right, so I should change the D1 pins, right, because that D1 pin corresponds to the control equal to 1, the D0 pins corresponds to the control equal to 0, that is what I did, and then I derived the logic for the D1 pin and the D0 pin of the both flip flops. So since as I said, right, so the library has a kind of a flip flop where the mux is inbuilt, and again that's what the tool also does. Yeah, good. Again it just right, so take this as a kind of input and then so just work it on later. Okay, I think this should be simple. So we will have a kind of a simple next state with a current state, yeah, with the kind of a passage of the clock. Okay, good. Now, okay, just look at the example. So now we can also have multiple clocks, right? Again, take a minute or two and then come up with a diagram for this, synthesize diagram for this. Yeah. And remember that one variable cannot be assigned in multiple, let us say, passage statements, right, and under the different clock. So if you look at here, right, so this add state is being assigned under this clock. Suppose this add state also will get assigned in another, let us say, always block with a different clock. Now you have a confusion, right, what should the clock should be connected to, that flip flop, right, what clock it should be get connected to, either the first one or the second one, that means it's wrong, right. If you have a confusion, the tool also will have a confusion, so it should not be the right thing. Okay, that means any variable which is on the left hand side in a passage of the clock or negation of the clock, I mean it should only appear only once in the left hand side, it cannot appear on the right hand, let us say left hand side multiple times, and then we have a problem, right, to which clock we should connect, that is the question. But I mean we can read under another clock, that is what is happening here, right. So here add state is being assigned in under one clock, but it is being read in a different clock, that is okay, right. So basically here you can expect that this add state, sub state are the flip flops with this VT5 clock, and maybe this DSL add and a DSL sub are kind of a flip flop which are clocked by this DSL clock, right? But of course, right, the DSL add will take the input from this add state. So try to draw the diagram on your own. So we should be kind of in time. We'll have an example for that. We have, I think. I'll show you. Yeah, I'll just show you the logic as I said, right? So that add state and substate are the kind of designs which are clocked by this VDFI clock, and then this is clocked by this DSL clock. Of course, right? This add state you are reading, right? So this DSL add. Okay, good. So now I think this is what I think Rahul was referring to. We can have, of course, right? Generally, the practice is that we will not use the positive and negative in both, but for the sake of having, right, we can just test, right? So here, how should be the diagram? I mean, there are, let's say, two, let's say, flops, and one flop is clocked by the positive of the clock, right? This CK. So this D or C, right? And it goes as input DQ, and this is your E. So CK is connected to CLK, right? So now the next one, the negative of clock, right? Yes, it's a AND. The DQ, and this is your D. Okay, and now of course D comes from where? So now you are reading this D and C, right? So the D should be connected to this D and this D are same. Yeah? Yes or no? Of course, both D should be the same, right? Okay. So this your, okay. So that's what we have here. So right, this D is a same D. Okay, just a different way of drawing, but it's exactly the same. Okay. I mean, both clocks was same, it's fine, but right. No, but again, you see, right, you're just I mean, this adds. So the problem is only with this one, right? So here, what is happening? It will be the same clock. You're just loading the previous value. That's all, right?
The current one will not be loaded.
Yes, the previous one. No, here also why the current one will load, right? It's if the clock was also same, it's difference, right? The clock was also same. What will happen? If the clocks are same, what will happen? So these two will also be clocked by this VT5 clock. But these are the same thing, right? You are also reading the add state value. Add state or the substate, it's again a flip flops values which are clocked by VT5 clock. Yeah, but again you see, right? So you are reading first, right? It's not like you use the current value, right? Yeah, of course. Yeah, that's what I'm saying. Only the clock will change. That's all. Nothing will change. It will give the same circuit. Only the clock will change. That's all. Right. So instead of this DSL clock, so the same VT5 clock will be there. Yeah.
Still the value is not assigned to add state, then what? So it will either take the one which is actually being resolved.
No, but you see, right? These are two executing in parallel, right? So now, right? So now you're trying to calculate a new value for it. Okay, you explain, right? But I'm just reading the previous value of the add state, right? That's what is this one here, right? The previous value you're reading. That's all. Huh? Good. Fine. Okay. Now, okay. So here I think I was trying to explain in this slide the same thing which I mentioned before. So whenever you have such a kind of the passage A, B, C, right. So in this if you see, right, you do not know which is the clock because we are using the names called A, B, C, right. So now the emphasis is that, okay, right. So we have to look at this statement and then what is the else block, what is left out. So in this case now we use A, right, B used, and of course C we used, and we did not use the CLOCK. So that should be your clock. Okay. Now again the same example, right. So what is the difference between the previous example and this example with the latches? I mean the example exactly looks the same, right, but only that, so now we have a negate of clock here, right. Earlier of course we have a passage reset or something and all, but so we have a passage of the negate of clock here. So again, so here is it like let's assume that we have a flip flop. So we can have a flip flop. Earlier what we said was, okay, maybe I can repeat, when we are synthesizing with the latches, right, we said we can have a latch with your preset and clear pins. So we can really redirect the logic, right, but we have only the CDN pin, right. So then we have to really appropriately redirect the logic to the D input, and in both cases we have to make the latch open. Yes or no? So here let us assume that we have a kind of a flip flop with both or any one of them, but we have kind of a latches, sorry, the flip flops with this preset and clear pins. So again what we need to do is that we need to really redirect this logic appropriately. Yes or no? Okay. So just let's just kind of try to really solve it again. I'll just I think I should have a solution. I just look for that. Yeah. Okay. So this is what we have. Okay. So for the next state 0, right. So we have, of course we are looking at this 0 and this one, right. Okay. So again we have a not reset. So that means 0 should be there, and set we do not care, right. Okay. And of course, right, now in this case we do not have a clock X because that is going to the clock itself, right. Okay. Now set could be anything, right, and then when you have a, let's say, reset equal to 1, so then only we look at the set value, right. So set should be 0, okay, and then we have a 1, this is 1 correspond to this one, and then reset equal to 1 and set equal to 1, and that is a clock condition, right. So then, so we will have current state equal to next state. So again what we need to do is that again in the, I think so we wanted to match the solution which is present in the book. Okay. So here I mean in general we can have a D flip flop with a preset pin, clear pin, and again the preset could be, let's say, active low, even the reset could be active low, but again as I said, if you look at the solution here used a flip flop with preset pin active high and the clear pin active high. So now here, so we have this 0 condition, right, and we have this 1 condition, right. So the preset or let's say the reset or a clear, right. So we should take this condition. Yeah. So what is that condition? So what is that condition? It should be a reset bar, right. Now if you see, if you connect the reset bar, what will happen? If the reset equal to 0, reset bar will be 1, and if you connect 1 to this CD pin, what will happen? Your output should be set to 0. Is that right? So similarly, now let us talk about the preset pin, right. This logic should go to the preset pin, right. So if you apply to that pin 1, so output should be set to 1, right. Okay. Now how do you get this logic? PD, right. So what is the condition we have? We have a set bar 0, right, it is a set bar and reset. So we have a set bar and reset, we are just connecting it. Again just look, right, if the reset equal to 1 and set bar, right, so set equal to 0, right, what will happen? So set bar 0 means bar set will be 1 and reset multiplied by set will be 1, and you are connecting it to the PD, right. So if you connect the PD equal to 1, what will happen? If the PD pin equal to 1, your output bit is set to 1, right? And then these two conditions you already covered, right? So what is left out with the clock condition, right? So right, so that one you, of course, clock is connected to the clock A, and so what is the input? It's a simple current state 0. Okay, so this way, right? So we can really derive for the next state as well. Okay, so again, just to give you a kind of thought process. So maybe you do it for the current state 1. At least just to give you a kind of a time. So do it for the current state 1. Okay. Good. So for the current state 1 flip flop, you just try to really derive the logic. So now in the current state, let's say next state 1 case, both the kind of a not reset or a set, right, is 0 0, right? So right, so we want reset to use only the CD pin. Okay, I mean again the CD pin could be active low or active high. So as thinking the CD pin is active high. So now that means these are the two conditions. Now you see, right, what are the conditions we can simply right? It's a not reset or not reset. Right? So again, if you see, right, it's also to kind of, if you are a bit confused in deriving the logic, so what we can also do is that we can also simplify for the CD with respect to with using K maps, right? For all the possible conditions you list it and then get the logic. Okay, and if it is a active low, what should do is that we should get a 0, right? So take this logic, whatever you come for the CD logic, just negate it, right? I mean this way, right? So any complicated logic can be done. Yeah, good. So let's move on. Okay, maybe when you get time, so do it for 2 and 3. Okay, okay. Now just okay, 1 second. Okay. So what is the difference between the previous circuit you have seen, this circuit? Huh? it's a synchronous reset and synchronous set. Okay, good. So now the idea here is that okay, now when you say it's a synchronous preset and synchronous clear, right? Okay, so now here I mean I could have a flip flop with a synchronous reset and a synchronous preset pins, but let's assume that I don't have a flip flop. That's what the solution says, right? I do not have a flip flop with synchronous reset and synchronous, let's say set. Yeah, now what should I do? I am left only with the whole logic. I should really redirect it to D input. Yes or no? Okay, so how do we really do that? So here, okay, so that's what we have. Okay, now try to look at what we are trying to really do. Okay, so anyway the clock B is there, right? Okay, so what we are trying to do is that, of course, if you look at maybe 12, right? 12 is 110 and 5 is 0101, right? I am talking about the next state 0, the first, let's say the flip flop. I am just trying to really put exactly the I mean kind of a bit high level view that, okay, of course I have to really synthesize a D flip flop for the next state 0, right? I am there. I know which clock I should connect it to, the clock B. Okay, now the question is, I mean of course everything is a reset, right? I mean everything is a synchronous, right? So I have only a D pin which is synchronous with respect to clock. That means I should really redirect everything to the D input itself. Okay, but again, right, so I have a kind of a priority here. Okay, now what I will do is that, so if you look as per the diagram, right, so I am taking a control signal as reset. If the reset equal to 0, what should I do? I send 0, right? 0, right? If the reset equal to 1, that means it's not active. I should look at maybe the set value. Again, if the set equal to 0, I should send 1. That's a 1. And of course, if both of them are not, let's say, active, I should send current state 0, right? So now later on look at the solution which is given in the slides, and the diagram is exactly matches, but this is a bit more high level. Is that clear? I think we have a glitch, I guess, online, but it's okay, I feel. So the difference is that earlier we were really directing the logic to the D pin and let's say the preset pin and a clear pin, or the or the PD pin and a CD pin according to the book. The reason is that they are asynchronous and we have a flip flop in the library which does that, but here it's a synchronous flip flop and we don't have a flip flop with a synchronous pins, right? So now D pin is only the synchronous with respect to the clock. So that means we have to really redirect all the reset and set logic to the D pin itself. That's what we did. Okay, that's the difference. Yeah, good. Okay, so now I think these examples you should be able to do it. Okay, so purposefully, so I mean I think this one you should be able to do it. Okay, so here we wanted to really show the difference between again you see, right, in any block, so there is a kind of a blocking here and a non-blocking here. The actual advice is that not to mix them, but now to tell you something with this example, so we just mixed it. So now try to come up with a logic diagram of your own of, let's say, this code. So you have to be a bit careful with respect to the right shift value. What right shift we should really have? Whether the right shift is I mean you try and then you will look at the solution and just try to understand where we might have done a mistake. That's the rule, right? But let's assume that we mixed it, and what will happen? And you know, the way you think and how the diagram comes, you try to come up with your own diagram. Hmm? Okay. So maybe you can check whether so touch doesn't respond. Okay. Okay. So now, so where is the right shift? Okay. Which value of right shift you used? Okay. Here the select first is okay. Right shift is there. First of all, ask this question: how many flip flops will have? 3, right? Do we have 3? Okay, good. So one is for the right shift, one is for the check stop, and one is for the select first. Okay, good. So now right shift logic is nothing but we have to right shift and of course AND gate, of course a strobe and right shift, na? So we have to update the value. So that's what we should have. We have, right? Okay, good. Now for the select first, okay. Now you are reading the right shift, na? So which right shift you are taking? Huh? I mean, what the semantic says, we have to really use, but because this statement is executing after this, right? It's a blocked. So even though the non-blocking is there, they have to execute after executing the blocking statement. So now you might have done that, okay, you might be taking the output from the right shift flip flop, but you should not take, but you should really take the latest value of the right shift. So that's what we are trying to really show here, right? So right, this is the latest value, right? So we are not taking from this point to, I mean, for the select first, right? We are taking the updated value. This you might have done mistake. That's what I am saying. Is it clear? Okay, good. Yeah. So maybe again, so try to come up with your own diagram. Now here, okay. So here, what right shift value we have to use? Either from the flip flop output or the updated value, right? I would say that we should use the updated value, right? So updated value is already, it's a right shift multiple, let's say AND gate with strobe, right? And of those things, right? So we should really take that one with X flag and calculate the select first. Okay, so you might have done that, okay, instead of let's say this one, you might have taken here. That is wrong. That's what I'm saying. Right? Yep. So try to draw the diagram for this one again. So how many flip flops we have? 2, right? One for, another for, okay. So does FCR output is used by the claim, right? Because you see, right? So FCR output should be really used by the claim, right? In one of the condition, yeah. So I think, right, it will look something like this, but again, if you use a flip flop without a mux or something, it look bit different structurally, but exactly the equation wise it should be correct. Okay, good. Now the blocking counterpart. So earlier, right, so you might be reading the previous value of FCR and all those things, right, but so here it would be different, right. So you need to really use the updated value of FCR. That would be the only the difference. Okay, good. Yeah. So okay, and again if you see, right, so and one more important thing which you can notice here, in earlier case we had both flip flops, right, FCR and claim, but now if you see here, so FCR of course it's on the left hand side, right. What we said, if it is a left hand side variable, we will get a flip flop, right. But now if you see, right, it's computed here, it's used, right, it's a kind of a temporary variable. So we don't really need kind of a flip flop for the, right, the FCR. So we only have the claim. Okay, good, right. So that's all I had, and these are the references, so which use, it's completely from the Bhaskar book, and again as I said, right, so I might have copied, the slides from different sources, and I don't own all the slides. Okay, so I mean, the last maybe, of course, right, maybe 2.5 hours, what we try to kind of impress on upon you is that, I mean, we'll always have a kind of a thinking that okay, the synthesis tools does something different, we might not be able to understand, right. The takeaway message is that if you can really do with a pen and paper, yeah, and the tool is also trying to do the same thing. And again as I said, right, not only you should think in terms of writing the logic, but you should also start thinking in terms of, if I write something, how does the circuit will come like. And as I said, in the hardware what we have, it's a wire, latch and flip flop, and there are clear rules. When does we get a wire, when does we get a latch, and when does we get a flip flop, right. So with that in mind, we can really write a code which is kind of a synthesizable and will not have any simulation and synthesis mismatch, right. Again there are some golden rules, right, again. So in modeling the combination logic, use only the blocking, sequential use only non-blocking, and again as I said, right, I mean use only always block for even combination logic, and list all the right hand side variables in the sensitivity list, and then of course, right, using the always blocks have an advantage that you have a advanced constructs like if, else, case and all, we can use it, right. If you use maybe assign, you should only use kind of a long expressions, but that's how it is. Okay, so that's all I have. Yeah, I mean like whatever with that we have learned about the FPGAs, about this Verilog and all, but it's a kind of a semester long course. So but we just try to give a kind of a glimpse of it. So if anybody need, so I think we can also talk in a later as well. Good.